Right now, a million miles from Earth, James Webb is locked onto something that should not exist. Tiny red dots, scattered across the oldest parts of space, glowing where the rules say nothing should. For years, no one could explain them. Soon, you will meet a black hole hiding behind a perfect mask, gas spinning at 600 miles a second, and the moment a cosmic monster gets caught shedding its disguise. If deep space amazes you, hit like and subscribe. Now hold on, we begin. In the summer of 2022, a team of astronomers crowded around their screens, waiting for the first real pictures from a telescope that cost $10 billion. James Webb had just unfolded its golden mirror a million miles from Earth. The first deep images came down from space, and they were stunning. Galaxies stretched back almost to the beginning of time. Everyone cheered. Then someone noticed the dot. They were tiny, they were red, and they were everywhere. Little crimson points of light scattered across the background like freckles on the face of the universe. At first, nobody paid much attention. The big galaxies were the prize. But the dots kept showing up. One image, another image, a different patch of sky entirely. Same red dots. That was strange. A telescope points at a specific slice of space. You expect different things in different directions. Yet these red specks appeared almost everywhere. Webb looked into the deep past. They had a weird sameness to them. The same tiny size, the same red color, as if someone had taken a red pen and dotted the early universe at random. The astronomers ran the images again, checking for a glitch. Cameras can leave marks. Dust on a sensor can fake a signal. Heat can create ghosts in the data. They checked all of it. The dots were real. They were actual objects, sitting billions of miles away, sending real light across the cosmos to Webb's mirror. So the team did what scientists do when they have no idea what they are looking at. They gave it a plain name. Little red dots. No fancy label. No Greek letters. Just a description of what their eyes saw. The plain name hid a serious problem. These dots glowed from the most distant parts of space Webb could reach. That distance matters in a way that bends your brain a little. Light is fast, but space is enormous. The light from these dots had been flying toward us for over 11 billion years. It left its source before the sun existed, before Earth existed. The dots were a snapshot of the universe as a baby, only a few 100 million years old. And in that baby universe, something was glowing red and bright that should not have been there yet. The astronomers compared the new images to old ones from the Hubble Space Telescope, which had stared at these same patches of sky for years. They searched for the dots in Hubble's pictures. Nothing. The dots were missing. The most famous telescope in history had looked right at this part of space and seen empty black. Webb looked at the exact same spot and found it sprinkled with red lights. An entire population of objects sitting in plain sight, completely invisible to every telescope humanity had ever built. Something out there was hiding, and it had been hiding well for a very long time, until a golden mirror in deep space finally caught it. The team had a choice: ignore the dots and chase the famous galaxies, or stop, turn around, and ask what these little red specks actually were. They turned around. What they found over the next 4 years would force them to question how the entire universe got built. But before any of that, they had to answer one simple question first. How did Hubble miss something Webb saw in its very first week? The Hubble Space Telescope is one of the greatest machines ever made. For over 30 years, it gave us our sharpest views of the cosmos. So when an entire crowd of red dots showed up in Webb's images and not in Hubble's, the obvious question was simple. How does the newer telescope beat the legend so completely? The answer comes down to one thing: color. Or to be exact, a kind of light your eyes cannot see. Light is bigger than what humans can see. The colors we know, red through violet, are only a thin slice of a much wider range. Past red sits infrared, a kind of light we feel as heat but cannot see. A warm campfire, your own body, a slice of pizza fresh from the oven, All of them glow in infrared. We just need the right eyes to catch it. Hubble was built mostly to see visible light, the same colors your eyes use. It can stretch a little way into infrared, but only a little. Think of it as a camera tuned for daylight colors. Webb is different. Webb was built almost entirely to see infrared. Its giant golden mirror, the size of a tennis court, soaks up heat light from the most distant corners of space. Where Hubble sees daylight colors, Webb sees the warm glow underneath. That single difference is why the dots appeared. Remember how far away these objects sit. Their light traveled more than 11 billion years to reach us. During that long trip, something happened to the light, something we will get to soon, that pushed it out of the colors Hubble could see and deep into infrared. By the time the light arrived, it had become exactly the kind of glow only Webb was built to catch. Hubble was staring straight at these dots the whole time. The light was hitting its mirror, but that light had shifted into a range Hubble was nearly blind to. So the dots stayed dark in every Hubble picture, like a person standing in a room lit only by heat, invisible to a normal camera, but glowing bright to a heat sensor. There was a second reason too. Size matters in space telescopes. A bigger mirror gathers more light and shows fainter things. Webb's mirror is far larger than Hubble's, which means it can spot objects too dim for the older telescope to register at all. Some of these dots are so faint that even if they glowed in visible light, Hubble might still have missed them in the noise. Put those two things together, the wrong color and not enough light, and Hubble never had a chance. The dots were a target perfectly designed to slip past it. For decades, an entire class of cosmic objects sat just beyond our reach, waiting for a telescope built for exactly this kind of light. When Webb launched, it did not just give us prettier pictures. It opened a door into a part of the universe we had never seen. And the moment that door swung open, the red dots came flooding through. So the astronomers now had thousands of these objects, glowing in infrared, scattered across the early universe. They could finally see them. Seeing something and understanding it are very different things. The next surprise was how the dots behaved when the team tried to figure out what they were made of, because the first guess turned out to be almost impossible. Imagine you are an astronomer with a fresh batch of images from the most advanced telescope ever built. You spot a tiny red dot. You want to know what it is. You cannot fly there. You cannot touch it. So how do you study something 11 billion years away? You read its light. Light carries secrets. When you spread it out, the way a prism splits sunlight into a rainbow, you get a kind of barcode. Different materials leave different marks in that barcode. Hot hydrogen makes one pattern, oxygen makes another. By studying the spread out light from a dot, scientists can figure out what it is made of, how hot it is, and how fast it is moving. So, the team took the red dots and spread their light apart. One by one, they wanted that barcode. The first thing they noticed was how packed the light was. These dots were small, incredibly small for how bright they shined. A normal galaxy spreads its glow across a huge region of space, the way a city spreads its lights across many miles. These dots crammed a galaxy's worth of light into a tiny point, like squeezing an entire city's glow down to the size of a single street lamp. That tightness was a giant clue, and it pointed somewhere strange. The early guess was that these were galaxies, very old, very distant galaxies, made of countless stars, all glowing together. The red color seemed to fit. Old starlight stretched across billions of years could look red, so the first papers called them dense early galaxies and tried to move on. The numbers refused to cooperate. If a dot was truly a galaxy made of stars, scientists could estimate how many stars it would need to shine that brightly from that far away. The answer was staggering. To pack that much starlight into that smaller space, you would need stars jammed together far tighter than anything we have ever seen. How tight? Picture our own neighborhood of the galaxy. The nearest star to our sun sits about 4 light years away, a distance so huge that a jet plane would take millions of years to cross it. Stars usually keep their distance. They drift through space with enormous gaps between them. Now, imagine cramming those stars together until the gaps almost vanish. Thousands of suns packed into a space where we would normally find one. A traffic jam of stars so dense that the night sky on any planet inside would blaze brighter than 100 of our own suns at once. That kind of star city should not be able to exist. Packed stars that tightly in gravity goes wild. They would crash, merge, and tear each other apart. The whole system would collapse. Our best models of how the universe builds things simply break when you try to make stars that crowded. So the astronomers were stuck with two impossible options. Either the universe had somehow built the densest, most crowded star systems ever imagined, breaking the rules of physics in the process, or the red dots were not made of stars at all, and something else entirely was producing all that light. Neither answer felt comfortable. One broke the math, the other meant a brand new kind of object hiding in the early universe. To break the tie, the team needed to look closer at the light itself. And buried inside that barcode was a detail that pointed at something far more dangerous than a crowded city of stars. The astronomers kept staring at the same impossible problem. The red dots were too bright and too tightly packed to be normal galaxies. Yet, if you tried to build them out of stars, the whole thing collapsed under its own gravity. So they went back to the light barcode, looking for any detail they had missed. They found one. The light was moving. Not moving across the sky. Moving in a way you can hear, in a sense, if you know how to read it. When something that glows races toward you or away from you, its light shifts. The same way a race car's engine changes pitch as it screams past you on a track. Coming closer, the sound rises. Moving away, it drops. Light does the same trick. Material rushing toward us looks slightly bluer. Material rushing away looks slightly redder. Inside the red dots, the light showed both at once. Part of the glow was shifted one way, part the other way. That meant whatever was producing the light had gas moving toward us and gas moving away from us at the same time, on opposite sides. Something in there was spinning fast, and the speed it showed was almost unbelievable. The gas was whipping around at over 600 miles every second. Slow down and feel that number. A rifle bullet travels around half a mile per second. A space rocket escaping Earth needs about 7 miles per second. This gas was moving at 600 miles per second, more than 80 times faster than a rocket tearing away from our planet. Fast enough to cross the entire United States, coast to coast, in about 4 seconds. Stars do not whip gas around like that. Something with monstrous gravity does. There is only one kind of object that spins material that fast in a space that small. A black hole. A region where so much mass is crushed into so little room that not even light can escape its pull. Gas falling toward a black hole speeds up the way water speeds up, swirling down a drain, faster and faster as it spirals inward, until it is racing around at hundreds of miles per second. The tight size suddenly made sense. The blazing brightness made sense. A black hole does not shine itself, but the gas crashing into it heats up so violently that it glows brighter than entire galaxies. All that light pouring out of a single point, exactly like the dots showed. These were not crowded cities of stars. Each red dot held a black hole at its heart, and not a small one. The gas speeds and the brightness pointed to giants, the kind of black hole we usually find sitting at the centers of grown-up galaxies, weighing millions of times more than our Sunday. The discovery should have been a victory. The team had cracked the mystery. The dots were giant black holes, feeding and glowing in the early universe. A new problem opened the moment they celebrated. Black holes are some of the loudest objects in the cosmos. When they feed, they scream across many kinds of light, blasting out signals that astronomers have used for decades to hunt them down. These signals are the fingerprints of a feeding black hole, almost impossible to hide. The red dots showed almost none of them. A giant black hole was sitting right there, glowing in infrared, yet staying completely silent in the very signals that should have given it away. Something was muffling the monster, and whatever it was had built a nearly perfect disguise. When a black hole feeds, it does not feed quietly. Gas spiraling into one gets squeezed and heated until it glows in almost every kind of light at once. The brightest signal of all comes in X-rays, the same high-energy light a hospital uses to photograph your bones. A feeding giant black hole usually blasts out a flood of X-rays so strong that astronomers can spot it from across the universe. For decades, that X-ray flash has been the number one way to hunt black holes. Find the X-rays, find the monster. It almost always works. The red dots broke the rule. When scientists checked them for X-rays, the signal was missing, or so faint it barely registered. Same story with radio waves. Another loud signal feeding black holes usually pump out. The dots stayed silent in both. A giant black hole was clearly glowing in infrared, yet it was hiding its two loudest fingerprints completely. It was like finding a roaring bonfire that gave off light but no heat. The pieces did not fit. A black hole big enough to shine that bright should be screaming in X-rays. So where did the scream go? The answer turned out to be a cocoon. These black holes are wrapped inside enormous clouds of gas, mostly hydrogen, the simplest and most common stuff in the universe. And these are not thin wisps. They are thick, dense walls of gas packed so tightly around the black hole that they trap most of the light trying to escape. Picture a flashlight inside a thick wool blanket. The flashlight is blazing, but wrap enough heavy fabric around it and almost no light gets out. Press your hand to the blanket and you might feel a warm glow seeping through, the heat that made it past the wool. The bright beam itself stays trapped inside. The hydrogen cocoon works the same way. The black hole at the center burns furiously, blasting X-rays and radio waves in every direction. But the thick gas swallows those signals before they can escape. The X-rays slam into the gas and get absorbed. The radio waves get tangled and lost. Almost nothing, high energy, makes it through the wall. One thing does escape: heat. All those trapped X-rays dump their energy into the gas, warming the entire cocoon until it glows. That warm glow leaks out into space as infrared light, the same heat light Webb was built to see. The blanket itself becomes the thing that shines. So Webb catches the warm outer glow of the cocoon, while the violent screaming core stays sealed inside, hidden from every X-ray telescope pointed its way. That is the perfect disguise. A giant black hole, one of the most violent objects that can exist, made nearly invisible by wrapping itself in a blanket of the most ordinary gas in the cosmos. For years it fooled us completely. We had the telescopes to find black holes. We just could not see these ones, because they had muffled their own alarm. The disguise was so good that even after scientists figured out the trick, one big question stayed wide open. We knew the gas hid the X-rays. We knew heat leaked out as the red glow. We still did not fully understand how the black hole turned that swallowed gas into so much light in the first place. To see that, you have to go inside the cocoon, down to where the gas meets the edge of the abyss. To understand why these hidden black holes glow so brightly, you have to follow a single piece of gas on its final journey. Picture one clump of hydrogen, floating inside the thick cocoon, drifting a little too close to the black hole at the center. Gravity grabs it. From that moment, the clump is doomed, and on its way down it is going to put on a show. A black hole does not suck things straight in like a vacuum. Gas falling toward one starts to circle, the way water circles a drain instead of dropping straight through. The clump of hydrogen begins to spin around the black hole, joining a vast flattened disk of other gas, all swirling in the same direction. Astronomers call this swirling pancake an accretion disk. You can just think of it as a whirlpool of doomed gas. As the clump spirals inward, it speeds up. Closer means faster. By the time it nears the edge, it is racing around at hundreds of miles per second. Part of that 600-mile-a-second storm the light barcode revealed. And here is where the glow comes from. In that whirlpool, gas does not all move at the same speed. The inner parts race faster than the outer parts, so layers of gas grind against each other, scraping and rubbing as they slide past. That grinding creates friction, the same way rubbing your hands together fast makes them warm, except this is not your hands. This is an entire galaxy's worth of gas, grinding against itself at brutal speeds. The friction heats the gas to temperatures that are hard to even picture. We are talking hundreds of thousands of degrees, far hotter than the surface of the Sunday. At those temperatures, matter does not just get warm, it blazes. It pours out light with incredible power, brighter than billions of stars combined, all from a region smaller than our solar system. That is the secret. The black hole itself is dark. The gas falling into it is the light bulb. As material grinds its way down toward the point of no return, it shines with the energy of a dying scream, blasting out light right up until the instant it vanishes past the edge forever. Once the gas crosses that edge, called the event horizon, it is gone. No light, no signal, nothing comes back. The clump of hydrogen we followed makes one last bright flare on its way in, and then it disappears from the universe completely, crushed down into the black hole and adding a tiny bit more to its mass. Multiply that by countless clumps of gas, all falling, all grinding, all flaring on their way down, and you get the blazing glow of a feeding black hole, a constant river of doomed material, lighting up as it dies. Now remember the cocoon wrapped around all of this. That blazing whirlpool sits buried inside the thick hydrogen blanket. The intense light slams into the surrounding gas, gets trapped, heats the blanket, and leaks out as the soft red glow Webb finally caught. The violence is sealed inside. Only the warm outer shimmer escapes into space. So, the red dots are powered by destruction. Each one is a black hole eating, and the light is the last flash of everything it swallows. That explains the glow. It does not explain the color, because the strangest thing about these dots is that their famous red shade has almost nothing to do with the gas, the heat, or the black hole at all. Everyone calls them the little red dots. The red is right there in the name, so it seems obvious that the color comes from the glowing gas, or the heat of the black hole, or something happening inside the cocoon. That guess feels natural. That guess is wrong. The deep red color is mostly an illusion, created by something far bigger than the black hole. It is created by the entire universe stretching. Here is the strange truth about space. The universe is not sitting still. It is growing. Every second, the space between distant galaxies gets a little wider. Galaxies are not flying apart through space like debris from an explosion. The space itself, the empty distance between everything, is swelling, carrying the galaxies along with it. Picture a balloon with dots drawn on it. Blow the balloon up. The dots all move away from each other, not because they are crawling across the rubber, but because the rubber itself is stretching between them. The universe does the same thing in 3 dimensions. Everything drifts apart because the space in between keeps expanding. Now think about light traveling through that stretching space. When light leaves one of these black holes, it starts out as a certain color, with a certain wavelength, the tiny distance between the peaks of the light wave. Then it begins its long journey toward Earth, 11 billion years of flying through expanding space. The whole time, the space the light is crossing keeps stretching, and as the space stretches, it pulls the light wave with it, spreading those peaks farther apart. Stretch a light wave out and its color changes. Longer waves look redder. So light that left the black hole as ordinary visible light, maybe even bluish-white, gets pulled and stretched over billions of years until it arrives at Earth as deep red or even invisible infrared. Scientists call this stretching redshift because the light shifts toward the red end of the rainbow. The farther away something is, the longer its light has been traveling, and the more the universe has stretched along the way. So the most distant objects show the strongest redshift. These black holes sit among the most distant things Webb can see, which means their light has been stretched about as far as stretching goes. That is why they all look the same shade of red. They are all roughly the same enormous distance away, so their light all got stretched by about the same amount. The uniform red color was a clue hiding in plain sight. It was the universe quietly telling us these objects are all incredibly far away and incredibly old. The redness is basically a distance tag, stamped onto the light by billions of years of cosmic expansion. That is why Hubble missed them, by the way. The stretching pushed their light out of the colors Hubble could see and into the infrared range only Webb could catch. The same expansion that paints them red is the same expansion that hid them for decades. So, the color is not really their color at all. It is a fingerprint of distance and time, written across the light during its long journey to us. Once you understand redshift, looking at these dots becomes something stranger than just looking far away. Because in space, looking far away means looking into the past. And these particular dots are showing us a moment in cosmic history that should have been far too early for monsters this big to exist. There is a fact about space that sounds like science fiction, but is completely true. When you look at distant objects, you are looking back in time. The farther you look, the deeper into the past you see. And this is not a trick or a metaphor. It happens because light takes time to travel. Light is fast, the fastest thing there is. But the universe is so vast that even light crawls across it. Light from the sun takes about 8 minutes to reach Earth. So when you glance at the sun, you see it as it was 8 minutes ago. If the sun vanished this instant, you would keep seeing it shining for 8 more minutes before the sky went dark. Push that idea outward and it gets dizzying. The nearest big galaxy to us, Andromeda, is so far that its light takes around 2.5 million years to arrive. Look at Andromeda tonight, and you see light that left it before modern humans even existed. You are staring into the deep past just by looking up. Webb takes this to the extreme. It is built to catch the faintest, most stretched out light in the cosmos, light that has been traveling for almost the entire age of the universe. When Webb looks at the red dots, it sees light that left them more than 11 billion years ago. So, Webb is a time machine. Point it far enough and it shows you the universe as a newborn. The universe is about 13.5 billion years old. The light from these dots has been flying for over 11 billion of those years. That means Webb is catching these black holes as they looked when the universe was only around 600 million years old. In cosmic terms, that is a baby. If you squeeze the whole history of the universe into a single year, these dots are glowing in the first few weeks of January. That timing is the problem. That timing is what makes scientists nervous. These are giant black holes, weighing millions of times more than the Sunday. And Webb is showing them already grown, already feeding, already huge. When the universe was barely getting started, they had almost no time to reach that size. Think about it like finding a fully grown oak tree in a field that was bare dirt last week. Big trees take decades to grow, so a giant oak appearing in days does not just surprise you. It tells you that you do not understand how trees grow at all. Either this one grew impossibly fast, or it did not start as a seedling the way you assumed. That is exactly the puzzle Webb dropped on astronomers. Giant black holes are supposed to take billions of years to grow. These ones were already giants when the universe was a few 100 million years old. The math does not add up. There simply was not enough time. So, either these black holes grew faster than anything we thought possible, breaking the rules we believed in, or they were born big, skipping the slow growth entirely through some process we have never seen. Both options rewrite the story of the early universe. Before chasing that down, scientists noticed something else about the dots, a pattern in time. The dots do not last forever. They switch on at a certain age of the universe, and then, hundreds of millions of years later, they start to vanish, and nobody knows where they go. When scientists mapped out the red dots by distance, they were really mapping them out by time. Closer dots show a later universe, farther dots show an earlier one. By sorting thousands of these objects, the team could build a kind of timeline, watching when the dots appeared and when they faded across cosmic history. A clear pattern jumped out. The dots had a beginning. Go back far enough to the youngest universe Webb can see, and there are very few dots. Then, around 600 million years after the universe began, they switch on in huge numbers. Suddenly, the early cosmos is sprinkled with them everywhere Webb looks. It is as if someone flipped a switch and lit up thousands of hidden black holes across the young universe all at once. That sudden arrival is a story by itself. Something about that moment, 600 million years in, made conditions just right for these cloaked monsters to form and feed. The universe had cooled enough, gathered enough gas, and pulled enough material together to build giant black holes wrapped in thick hydrogen blankets. Webb shows them blinking on across the sky like distant red streetlights coming alive at dusk. For a while, they thrive. The early universe is full of them, all feeding, all glowing, all hidden inside their cocoons. If you lived back then and had the right eyes, the deep sky would shimmer with these red points everywhere you turned. Then comes the part nobody expected. The dots start to disappear. Around 1.5 billion years after the universe began, the population of red dots drops off a cliff. Move forward in time and there are fewer and fewer of them. Keep going and they nearly vanish from the record. By the time you reach the modern universe, the era we live in, the little red dots are basically gone. We do not see them around us today. That vanishing act is a genuine mystery. These were thousands of giant black holes glowing across the early universe. Black holes do not just evaporate. They do not pack up and leave. So where did they all go? There are guesses. One idea is that the dots did not disappear at all. They simply changed. The thick hydrogen cocoon hiding each black hole might get used up over time, eaten by the black hole or blown away by its own violent energy. Strip away the blanket, and the object stops looking like a little red dot. It turns into a normal, exposed black hole sitting at the center of a growing galaxy. The dots would not be gone. They would have grown up into the ordinary giant black holes we see in galaxies today, including the one at the center of our own. Another idea is that something shut them down. Maybe the black holes ran out of nearby gas to feed on. With nothing left to swallow, the glow fades, the cocoon settles, and the bright red beacon goes dark. The black hole stays, but it stops shining. Both ideas are reasonable. Neither is proven. The exact reason these dots faded from the universe is still an open question, one of several the discovery left behind. While arguing about why the dots vanish, the team tried something new. They had been looking at the dots in infrared, where they appear as neat, calm red points. So they switched to a different kind of light to get a sharper view. What they saw in ultraviolet shattered the idea that these dots were calm at all. Up to this point, the red dots looked almost peaceful. In Webb's infrared images, each one shows up as a tidy little point of light, round and smooth, sitting quietly in the dark. Neat, simple, easy to picture as a single object glowing far away. That calm appearance shaped how scientists imagined them as compact, orderly balls of gas around a hidden black hole. So the team decided to look at the same dots in a different kind of light. Instead of infrared heat light, they examined the dots in ultraviolet, a higher energy light beyond the violet end of the rainbow. Ultraviolet is the same light that gives you a sunburn. It reveals different details than infrared does, often showing the most energetic, violent activity in an object. They gathered nearly 100 of the red dots and studied them under this sharper ultraviolet view, expecting to see the same calm points, just in a different color. What came back was chaos. About 30 out of every 100 dots were not neat points at all in ultraviolet. They were a mess. Instead of clean round dots, they appeared as fuzzy, smeared, irregular blotches, lopsided, stretched, torn looking, as if someone had taken a sharp dot and smudged it with a thumb while the paint was still wet. That smearing means something. A neat, round shape suggests one calm object sitting alone. A smeared, irregular shape suggests violence, motion, things crashing and tearing in ways a single quiet black hole would not cause. Roughly a third of these dots were hiding turmoil that only ultraviolet light could reveal. So what causes the chaos? The leading idea is collisions. The early universe was a crowded, messy place. Galaxies and clumps of gas sat much closer together than they do now, because the universe was smaller and everything was packed tighter. In that cramped early cosmos, Crashes were common. Whole galaxies smashed into each other. Streams of gas slammed together. The young universe was a demolition derby compared to the calm, spread-out cosmos of today. If one of these hidden black holes sat in the middle of a galaxy crash, the result would look exactly like those smeared ultraviolet blotches. Two galaxies merging would yank stars and gas in wild directions, stretching the light into lopsided shapes. The violence of the collision would show up as chaos in ultraviolet, even while the calm infrared glow of the cocoon stayed round and smooth. There is another possible cause too. The early universe made enormous stars, far bigger than most stars today. If a swarm of giant young stars crashed into the outer edges of the black hole's gas disk, that pileup could also smear the dot, lighting up the ultraviolet view with the glow of stars colliding into the whirlpool of doomed gas. Either way, the calm picture was a lie. At least a third of these dots are sitting inside some of the most violent events the early universe could produce. The smooth red point we see in infrared is just the quiet outer shell. Switch to ultraviolet, and the storm underneath shows through. That discovery raised an even stranger question. If 30 out of every 100 dots show this chaos, what about the other 70? Because the rest of them stayed perfectly calm in every kind of light the team tried. And that calm turned out to be just as confusing as the chaos. The ultraviolet study split the red dots into two camps. About 30 out of every 100 turned into smeared, violent blotches, hinting at crashes and chaos. That left the other 70. And those 70 did something that bothered scientists even more. They stayed perfectly calm. No matter what kind of light the team used, these dots refused to smear. In infrared, they were neat round points. In ultraviolet, the same neat round points. The light that tore the other dots into messy blotches did nothing to these. They sat in the data, looking smooth, compact, and completely undisturbed, like they had no idea the early universe was a violent place at all. At first, calm sounds like the easy case. A quiet dot seems simpler than a chaotic one. The calm is exactly what makes them hard to explain. Think about everything we have learned about these objects. Each one holds a giant black hole, feeding furiously, blasting out enough energy to glow across 11 billion years of space. Gas is whipping around it at 600 miles per second. The early universe around it is crowded, crash-prone, and chaotic. By every measure, these should be violent places. So, why do 70 out of every 100 look so peaceful? If collisions cause the smeared dots, then the calm dots should be the ones not having collisions. Fine, that part makes sense on its own. The deeper question is why some of these black holes sit in the middle of galaxy crashes, while others, in the same early universe, in the same crowded conditions, seem to sit completely alone and undisturbed. Same kind of object, same era, wildly different surroundings. Nobody has a clean explanation for the split. There is another puzzle hiding in the calm. A perfectly round, compact dot in every kind of light means the black hole and its cocoon are extremely smooth and even. The thick hydrogen blanket is wrapped so neatly that no detail leaks through, no matter how the team looks. That kind of perfect, undisturbed cocoon is strange for an object that is supposedly feeding hard enough to shine that bright. Violent feeding tends to make a mess. These calm dots show none of it. So the team is left with two groups, and neither fully makes sense. The chaotic dots are violent in ways that hint at crashes and merging galaxies. The calm dots are smooth in ways that seem too peaceful for what is happening inside them. Same population of objects, behaving in two completely different ways, and no clear rule for which dot does which. It would be easier if all the dots looked the same. Then scientists could build one story to explain them all. Instead, the dots seem to be telling two different stories at once, and the team cannot yet say why. The 30 chaotic dots and the 70 calm dots might be the same kind of object at different stages of life. Or they might be two different kinds of object that just happen to look alike from 11 billion years away. The data cannot yet tell us which. This split is one of the biggest open puzzles in the whole mystery. We can see the difference clearly. We just cannot explain it. For years, every red dot kept its X-ray scream sealed inside its gas cocoon, calm or chaotic, all of them silent in high-energy light. Then a single dot did something none of the others had done. It glowed in X-rays. And that one exception cracked the case wide open. For a long time, the silence was total. Every red dot kept its X-rays sealed inside its hydrogen cocoon. That silence was the whole disguise. The reason these black holes hid for so long. Astronomers had a hunch about what was happening inside the cocoons, but a hunch is not proof. To prove it, they needed to catch a black hole in the middle of changing. They needed one dot to break the silence. So NASA brought in a different telescope, one built for exactly the signal the dots were hiding. The Chandra X-ray Observatory is a space telescope designed to see only X-rays, the high-energy light that feeding black holes blast out and that the gas cocoons were trapping. Where Webb sees warm infrared glow, Chandra sees the violent X-ray scream. The team pointed Chandra at the red dots, hunting for any sign of X-rays leaking out. For most of the dots, Chandra saw nothing, just as expected. The cocoons were doing their job, swallowing the X-rays before they could escape. Dot after dot stayed silent. Then Chandra found one that was screaming. A single red dot, far out in the deep universe, was glowing in X-rays. Real, high-energy X-ray light, pouring out of a dot that should have been muffled like all the others. Out of the whole hidden population, this one had broken the pattern. Its scream was leaking out into space, and Chandra caught it. This dot got a name from its place in the sky survey, a long string of letters and numbers. We can just call it the screaming dot. It sits 11.8 billion light-years away, near the very edge of what our telescopes can reach. Its light left it when the universe was extremely young, which means whatever is happening to it happened in the deep early cosmos. That one screaming dot was the missing piece. It was a black hole caught in the act of revealing itself. Here is what scientists think is going on inside it. Remember the thick hydrogen blanket wrapped around each black hole, the cocoon that traps the X-rays and lets only heat escape. That blanket is not permanent. As the black hole feeds, it eats through the gas around it. It also blasts out energy that pushes the gas away. Over time, the smooth cocoon starts to wear thin in places. Gaps form, holes open up in the blanket. Once a hole opens, the trapped X-rays finally have a way out. They stream through the gap and escape into open space, where a telescope like Chandra can catch them. The black hole is still wrapped in most of its cocoon, but now it is leaking. The disguise is starting to fail. That is why this one dot glows in X-rays, while the others stay dark. The silent dots still have their cocoons fully intact, sealing everything inside. The screaming dot has worn its blanket thin enough that the scream is breaking through. It is the same kind of object as all the others, just caught at a later, more revealing stage. Finding this dot was like finding a single photo of a creature mid-transformation, frozen halfway between one form and the next. It proves the change is real, and it shows us exactly how the disguise comes undone. To see what this screaming dot is actually turning into, you have to understand what waits on the other side of that transformation. The screaming dot, caught by Chandra, was doing something the others were not. Its X-rays were leaking out through gaps in the gas cocoon. To understand why that matters so much, you have to see where this transformation leads. The screaming dot is a black hole in the middle of becoming something we already know very well. It is becoming a normal supermassive black hole, the kind that sits at the center of nearly every big galaxy, including ours. Here is the journey, start to finish. A red dot begins as a giant black hole wrapped in a thick hydrogen cocoon. The cocoon traps the X-rays and lets only heat escape, so the object glows soft and red and stays silent in high-energy light. That is the hidden phase, the disguise. Most of the dots Webb sees are stuck here, sealed inside their blankets. Then the black hole feeds. It eats through the gas around it and blasts the rest away with its own energy. Slowly, the cocoon thins. Gaps open. The screaming dot is right here, in the messy middle, with X-rays just starting to leak through the holes in its fading blanket. It is half hidden, half exposed, caught between two forms. If you let that process keep going, the cocoon eventually clears almost completely. The trapped X-rays pour out freely now. The radio waves escape. The black hole stops looking like a soft red dot and starts looking like a fully exposed, loudly screaming supermassive black hole, naked in the center of its galaxy. The disguise is gone. The monster stands revealed. That final form is something astronomers know inside and out. We have studied these exposed giant black holes for decades. We can see them blasting X-rays, firing jets of energy, lighting up the centers of galaxies across the universe. Our own galaxy, the Milky Way, has one at its heart, a giant black hole weighing about 4 million times more than the Sunday. It sits quietly now, but it is there, anchoring the center of everything we call home. The red dots, scientists now believe, are the babies of these familiar giants. The screaming dot shows us the in-between moment, the toddler years, when the black hole is shedding its baby blanket and growing into the adult form we recognize. Watch enough dots at different stages, and you can almost assemble the whole life story, from hidden red infant to exposed adult giant. That connection is huge. It means the mysterious red dots are not some weird dead end, some strange object that appeared and vanished for no reason. They are an early chapter in a story that ends with the giant black holes we see all around us today. The dots that faded from the universe did not truly disappear. Many of them grew up, threw off their cocoons, and became the ordinary supermassive black holes anchoring modern galaxies. So when you look at the screaming dot, you are looking at your own galaxy's distant past. The black hole at the center of the Milky Way may have started exactly like this, as a hidden red point wrapped in hydrogen, slowly burning through its cocoon until it broke free. The screaming dot answered how the disguise comes off. It opened a far bigger question about size, because these black holes are enormous, and they reached that size at a moment in cosmic history when, by every rule we know, they should still have been small. The screaming dot showed us how a red dot transforms into a familiar giant black hole. That answer led straight into a much harder problem. These black holes are huge, far too huge for how early they appear, and that size is breaking one of the most basic stories we tell about the universe. Start with how big they actually are. The black holes inside the red dots weigh somewhere between 100,000 and 10 million times the mass of our Sunday. Take a moment with the bigger end of that, 10 million suns, crushed into a single point, hidden inside one tiny red dot 11 billion light years away. Our sun is already almost impossible to picture. You could fit over 1 million Earths inside it. Now imagine 10 million of those suns, all packed together into one black hole. These are not small objects that happen to glow. They are monsters, among the heaviest single things the universe can build. By itself, a giant black hole is not shocking. We see 10 million sun black holes in the modern universe all the time. The shock is when these ones existed. Webb shows them already this massive when the universe was only around 600 million years old, a tiny fraction of its current age. That is the problem in one sentence. They are too big, too early. To see why that breaks the rules, you need the standard story of how black holes are supposed to grow. For a long time, scientists believed every giant black hole started small. A big star runs out of fuel, collapses, and forms a small black hole, maybe a few times the mass of the Sunday. That little black hole then begins to feed, swallowing gas and stars, slowly gaining weight over enormous spans of time. It might also merge with other black holes, combining into something larger. Bit by bit, over billions of years, that small seed grows into a giant, like a snowball rolling downhill, starting tiny and gathering mass the whole way down. The key word is slowly. In the standard story, building a 10 million sun black hole takes a very long time because it has to grow one mouthful of gas at a time. The red dots had no time. The universe was only 600 million years old. There simply were not enough years for a small seed to feed and merge its way up to 10 million suns. Even feeding as fast as physics allows, the math falls short. A black hole can only swallow gas so quickly before the light from that feeding pushes the rest of the gas away, choking off its own meal. There is a speed limit on growth, and the standard story cannot beat the clock. So, the rules say these black holes should be small at this age. Webb says they are giant. Both cannot be true. Either the rules are wrong, or the story of how black holes grow is missing something major. That collision between the rules and the evidence is exactly what makes this discovery so disruptive. It is not a small correction. It pokes a hole in our basic understanding of how the first giant objects in the universe came to be. If a slow-growing snowball cannot explain these black holes, then something else must. And the leading idea is almost stranger than the dots themselves. Some of these black holes may have skipped the small stage completely and been born as giants from the very start. If a black hole cannot grow from a tiny seed into a giant fast enough, there is only one way left to explain the red dots. Skip the slow growth entirely. Do not start small at all. Start big. This is the leading idea for the red dots, and it flips the old story upside down. Instead of a small black hole slowly fattening up over billions of years, scientists think some of these giants were born huge, collapsing directly out of enormous streams of gas in one dramatic step. Here is how that could work. The early universe was flooded with gas, mostly hydrogen, the simplest stuff there is. In certain spots, gravity pulled this gas together into gigantic streams and clouds, far larger than anything that forms stars today. Normally, a big cloud of gas like this would break apart into many pieces, and each piece would collapse into a star. You would get a cluster of stars instead of one giant object. In a few rare places in the early universe, conditions may have stopped that from happening. The gas did not break into pieces. Instead, an enormous cloud collapsed all at once, straight down into a single object, without bothering to become stars first. The result would be a black hole born already weighing tens of thousands, or even hundreds of thousands of times the mass of the Sun, right from the start. Scientists call these direct collapse black holes because the gas collapses directly into a black hole, skipping the usual steps. Think of the old story as filling a bucket one drop at a time. The new story dumps the whole bucket in at once. One process is slow and gradual. The other is instant and enormous. A black hole born that big has a massive head start. Start at 100,000 suns instead of a handful, and you do not need billions of years to reach 10 million. You are already most of the way there on day one. Give that head start a few 100 million years of heavy feeding inside a thick gas cocoon, and you can build the giant black holes Webb sees in the early universe. The timeline finally works. That solves the size problem. It does not come free. Direct collapse needs very specific, very rare conditions to happen at all. The gas has to stay smooth and avoid breaking into stars, which is hard. Something has to keep the cloud from cooling and fragmenting the normal way. Scientists have ideas about how this could happen, but we have never actually watched it occur. It remains a strong theory, not a confirmed fact. Still, the red dots are some of the best evidence we have ever found that direct collapse might be real. If these black holes truly were born giant, then the early universe had a way of making monsters from scratch, fully formed, without the slow climb. That would mean the first giant black holes did not wait around. They arrived early and massive, ready to shape everything that came after. And shaping everything is exactly what they may have done, because giant black holes are not just passive objects sitting in space. They may have played a key role in building the first galaxies, acting like anchors that pulled the early universe into the shapes we see today. That idea takes the red dots from a strange mystery to something much bigger. They might be part of the reason galaxies exist at all. So far, the red dots have been a puzzle to solve. Now they become something more important. These early black holes may not have just sat in the young universe glowing. They may have helped build the galaxies around them, acting as anchors that shape the cosmos we live in today. To see how, look at galaxies right now. Nearly every big galaxy has a giant black hole at its center. Our Milky Way has one. The galaxies next door have them. Look anywhere with a giant galaxy, and you almost always find a giant black hole sitting at its heart. That pattern is everywhere, and patterns that common usually mean something. For a long time, scientists figured the galaxy came first, and the black hole grew up inside it later, like a pearl forming inside an oyster. The red dots flip that thinking. They show giant black holes existing extremely early, possibly before their galaxies had fully formed around them. That raises a wild possibility. Maybe the black hole came first, and the galaxy built itself around the black hole. Here is how that could work. A giant black hole has enormous gravity, reaching far out into space. Drop one of these monsters into the early universe, and it becomes a center of pull, a gravitational anchor. Gas and matter drifting nearby feel that pull and start to gather around it. Over time, all that gathering gas could form stars, and those stars could build up into a galaxy, with the black hole sitting at the center the whole time, holding everything together. Picture dropping a heavy weight onto a stretched rubber sheet. The weight creates a dip, and anything rolling nearby spirals in toward it. A giant early black hole could act like that weight, creating a deep gravitational dip that pulled the surrounding universe inward, gathering the material that would become a galaxy. The black hole would be the seed, and the galaxy would grow around it. If that is true, then the red dots are showing us galaxies in the middle of being born, with the black hole engine already running at the center. The thick gas cocoon around each dot would be the raw material, the same gas that could go on to form stars once the violence settled down. We might be watching the very first step of galaxy building, frozen 11 billion years in the past. This would explain that strange pattern we see today, the way nearly every big galaxy has a giant black hole that matches it in size. Bigger galaxies tend to have bigger central black holes in a tight relationship that has puzzled scientists for years. If black holes and galaxies grew up together from the start, each shaping the other, that close match would make sense. They are partners, locked together since the beginning. It is a big claim, and it is not settled. We cannot yet prove the black hole came first in these systems, or that it truly anchored the galaxy around it. The red dots are some of the strongest hints we have, but hints are not certainty. The exact relationship between these early black holes and the galaxies that may have grown around them is still being worked out. What is clear is that these little red dots are no minor side note. They sit close to one of the biggest questions in all of science. How did the universe go from smooth gas to the grand structure of galaxies we see today? The red dots gave us pieces of that answer. They also left behind a pile of questions Webb still cannot solve, and the hunt to crack them is only beginning. After 4 years of study, the red dots have gone from a total mystery to something we mostly understand. We know they are giant black holes hiding inside thick hydrogen cocoons. We know why they glow red, why Hubble missed them, and how they shed their disguise to become familiar giants. That is real progress. The dots also left behind a stack of questions that nobody can answer yet, and some of them cut deep. Start with the vanishing act. The dots switch on about 600 million years after the universe began, thrive for a while, then drop off sharply around 1.5 billion years in. We have guesses about why. Maybe they grew up into normal black holes. Maybe they ran out of gas to feed on. We do not actually know which, or whether both happen, or whether something else entirely shuts them down. The exact reason a whole population of black holes faded from the universe is still unsolved. Then there is the split personality of the dots. About 30 out of every 100 turn violent and smeared in ultraviolet light, hinting at crashes, and merging galaxies. The other 70 stay perfectly calm in every kind of light we try. Same type of object, same era, two completely different behaviors. Nobody can explain why some go chaotic while others stay smooth. The rule that decides which dot does which is a complete blank. The biggest open question is how these black holes got so massive so fast. The direct collapse idea, where they were born giant from collapsing gas clouds, is the best answer we have. We have never actually watched a direct collapse happen. We do not fully understand the conditions it needs, or how common it was, or whether it can really explain all the dots or just some of them. The whole origin story rests on a process we believe in but have never seen. There is also a stranger theory still floating around, one that some scientists take seriously. A few of the dots might not be ordinary black holes at all. They might be a bizarre object where a black hole forms inside a giant star and eats it from the inside out, glowing so brightly it mimics a whole galaxy. Whether any of the dots are actually this strange beast is completely unproven, but it has not been ruled out either. Every one of these questions points to the same truth. We caught the universe doing something we did not expect, and we are still scrambling to understand it. The red dots forced scientists to rethink how the first giant black holes formed, how fast they grew, and how galaxies got their start. A discovery that big does not wrap up neatly. It opens more doors than it closes. The hunt is far from over. New studies are pointing more telescopes at these dots, gathering sharper data, trying to catch more of them mid-transformation like the screaming dot Chandra found. Each new observation chips away at the mystery, and each answer tends to raise fresh questions. That is how the early universe gives up its secrets. Slowly, one stubborn clue at a time. What started as a few odd red specks photobombing Webb's first images has grown into one of the most important puzzles in modern astronomy. These tiny dots may hold the story of how the universe built its first monsters and how those monsters helped build everything else. We have come a long way through this story already. The strangest, most extreme parts of it are still ahead. Most scientists now agree the red dots are giant black holes hiding in gas. A small group thinks something stranger might be going on inside, at least a few of them. Their idea sounds made up, but real researchers take it seriously. Some of these dots, they say, might be black hole stars. A black hole star is a creature that should not be possible, and yet the math allows it. Picture a giant star, far bigger than our sun, the kind the early universe loved to make. Now, picture a black hole forming right inside its core, deep in the center where the pressure is crushing. Instead of blowing the star apart, the black hole stays buried, hidden inside layer after layer of glowing gas. Then it starts to eat. The black hole at the heart of the star begins swallowing the star from the inside out. It feeds on the very thing it lives in, gulping down the star's own material as it falls inward. All that feeding releases a flood of energy, and that energy pushes outward through the star, making the whole giant ball blaze with light. From far away, the glow looks so bright and so concentrated that it could fool you into thinking you were seeing an entire galaxy. That is the trick. A single black hole star, eating its host from within, could shine like a galaxy made of millions of stars, while actually being just one strange object. If some red dots are these creatures, that would explain why they pack a galaxy's worth of light into such a tiny point. The light is not coming from countless stars. It is coming from one monster devouring its own body. Think of it like a campfire with something hidden in the middle of the logs, eating the wood from inside and making the whole pile burn far brighter than the wood ever could on its own. You see a blazing fire. You do not see the thing feeding at its core. The black hole star idea is attractive for one big reason. It offers another way to make these objects look so bright and so small without breaking the rules. A black hole buried in a giant star feeds in a protected, steady way, growing while the star feeds it from inside. That could let a black hole bulk up fast in the early universe, helping solve the puzzle of how the dots got so massive so quickly. There is a catch, and it is a serious one. Nobody has ever confirmed a black hole star exists. The whole idea lives on the edge of theory. It works on paper, in computer models, in the imaginations of scientists who run the numbers. We have never pointed a telescope at one and proven it is real. So while a few red dots might be these bizarre half-star, half-black hole hybrids that claim sits firmly in the land of maybe, most researchers still bet on the simpler answer that the dots are growing black holes wrapped in hydrogen. The black hole star theory keeps hanging around because the dots are weird enough that the normal explanation might not cover all of them. When an object breaks this many rules, scientists keep every strange idea on the table. Whichever answer wins, the light from these dots holds the proof. And when scientists spread that light apart to read it, they found a shape in it that no one fully understands. Every answer about the red dots comes from one place: their light. To study an object 11 billion light years away, scientists spread its light into a barcode, the same way a prism splits sunlight into a rainbow. That barcode shows what the object is made of and how it behaves. When the team made these barcodes for the red dots, the shape that came back was bizarre. Most objects in space make a barcode that slopes in a smooth, predictable way. The red dots make a shape that bends sharply, like a checkmark. Scientists describe it as a V shape. On one side, the light is faint and dim. Then it hits a turning point and shoots upward, getting much brighter toward the red end. That sudden bend is strange, and it does not match a normal galaxy or a normal black hole. The dim side and the bright side seem to come from two different things happening at once. The faint blue side appears to be a small amount of light leaking out from young stars or from the edges of the black hole's surroundings, barely escaping the thick gas. It is weak, almost drowned out. Then comes the sharp turn, and the red side blazes up, carrying the heavy infrared glow of the buried, feeding monster shining through its hydrogen blanket. Two sources, one faint and one strong, joined at a hard bend in the middle. That bend has a name. Scientists call it a break. A spot where the light suddenly changes character. In the red dots, this break sits in a place and shape that puzzles researchers because the usual explanations for it do not quite fit. The light is telling them something about the gas, the stars, and the black hole all tangled together, and they are still working out how to read the message. Here is why the shape matters so much. That sharp V is now a fingerprint. When scientists find an object with this exact bent barcode, they can flag it as a likely little red dot, even before they know anything else about it. The weird shape became a search tool, a way to hunt for more of these objects across Webb's images. Find the V, and you have probably found another hidden black hole. The fingerprint also rules things out. A normal cluster of stars would not make this shape. A normal exposed black hole would not make it either. The V only appears when you have a feeding black hole buried in thick gas, with a thin trickle of other light escaping alongside it. That is strong evidence the dots really are cloaked monsters and not some ordinary object we already understood. Still, the barcode keeps a few secrets. The exact reason the break sits where it does, the exact mix of gas and stars and black hole light producing the shape, remains under debate. Different teams read the same V slightly differently. Some see more starlight in it, some see almost pure black hole. The light is clear enough to point at a hidden monster, but blurry enough to leave the details up for argument. What everyone agrees on is that the shape is real, and the shape is strange. An entire population of objects, all showing the same odd bent light, all from the same era of the early universe. That kind of matching pattern almost never happens by accident. Reading the barcode closely revealed something else. Something about the dots that breaks one of the most reliable rules in all of astronomy. There is a rule in astronomy so steady that scientists trusted it for decades. The bigger a galaxy, the bigger the black hole at its center. Measure one, and you can guess the other. Across the modern universe, this relationship holds almost everywhere you look. A giant galaxy carries a giant central black hole. A smaller galaxy carries a smaller one. They scale together, like a person and their shadow. The red dots break that rule, and they break it hard. When scientists measured the black holes inside these dots, they came out enormous, up to 10 million times the mass of the Sunday. Then the team looked for the galaxy that should surround such a giant black hole. They expected a big, bright sea of stars to match the monster at the center. The galaxy was barely there. The black holes inside the red dots are gigantic, but the starlight around them is faint and small, far too little for a black hole that size. In the modern universe, a black hole this big would sit inside a massive galaxy packed with stars. In the red dots, the black hole seems to make up a huge fraction of the entire object, with almost no proper galaxy around it. The shadow is normal-sized. The thing casting it is a giant. Scientists call these overmassive black holes because the black hole is far too big for the tiny amount of galaxy it lives in. Picture a small backyard shed with a jet engine bolted inside, an engine built for a passenger plane. The engine dwarfs the building holding it. That mismatch is what the red dots show. The engine arrived first and oversized, and the building never caught up. This wrecks the neat idea that black holes and galaxies always grow together in lockstep. In the red dots, the black hole raced ahead. It grew massive while its galaxy stayed small, breaking the tidy match we see everywhere today. Something let these black holes balloon to giant size long before their galaxies could fill in around them. That points back to the wild origin story from earlier. The idea that these black holes were born big. If a black hole collapses straight out of a giant gas cloud, fully formed and massive, it would naturally be too big for its surroundings at first. The galaxy would have to play catch-up, slowly building stars over millions of years while the oversized black hole already sat at the center. The dots might be showing us that exact moment, the awkward early phase when the black hole leads and the galaxy lags far behind. If that is right, then the famous rule, the one tying black hole size to galaxy size, is not a starting condition at all. It is an ending. Black holes and galaxies might begin badly matched, with the black hole way ahead, and only grow into balance over billions of years. The red dots would be the before picture, and the galaxies around us would be the after. That idea is still being tested. Measuring faint starlight from 11 billion light-years away is brutally hard, and some of those tiny galaxies might be bigger than they look, hidden in the glare of the black hole. The overmassive puzzle is real, but its full meaning is not settled. One thing about these black holes is even harder to swallow than their size. It is the speed they would have needed to grow, a speed that slams straight into a hard limit built into physics itself. A black hole cannot eat as fast as it wants. That sounds backward, since a black hole is the hungriest thing in the universe. Physics puts a speed limit on how fast any black hole can feed, and that limit is the heart of the red dot problem. Here is why the limit exists. When a black hole feeds, the gas falling in heats up and blazes with light. That light pushes outward, shoving against the gas, still trying to fall in. Feed too fast, and the light gets so intense that it blows the incoming gas away, like a strong wind blowing leaves back before they can land. The black hole basically chokes on its own brightness. The harder it tries to eat, the more it shoves its own food out of reach. Scientists call this ceiling the feeding limit. It sets the fastest pace a black hole can gain weight while still glowing in the normal way. A black hole growing at this top speed doubles its mass roughly every few tens of millions of years, which sounds quick until you remember the math we are up against. Run the numbers on the red dots and the limit becomes a wall. To grow a 10 million sun black hole from a small seed, even feeding at the absolute maximum the whole time, would take far longer than the early universe had available. The clock ran out before the black hole could finish growing. Either the seed started much bigger than a normal star black hole, or the black hole found a way to break the speed limit and feed faster than physics is supposed to allow. Both options are wild. Both might be happening. The born big idea handles it by giving the black hole a giant head start, so it never needed to race. The other idea is stranger. Maybe these early black holes really did feed faster than the limit. In short, furious bursts. Scientists call this superfeeding, when a black hole gulps down gas so quickly that it briefly beats the ceiling, stuffing itself before its own light can push the gas away. How could that work? In the early universe, gas was thicker and packed tighter than it is today. If enough gas crowds in fast enough from every direction, it might overwhelm the outward push of light and keep pouring into the black hole, force-feeding it past the normal limit. The thick hydrogen cocoon around each dot could even help, trapping the light and weakening its ability to blow the gas back. The disguise that hides the X-rays might also be the thing that lets the black hole eat so fast. That would tie the whole story together neatly. The cocoon hides the black hole, traps its X-rays, makes it glow red, and lets it feed faster than physics normally permits, all at once. One thick blanket of gas, doing several strange jobs at the same time. We have not proven any black hole truly feeds past the limit for long. Short bursts might be possible, but sustaining it for hundreds of millions of years is a stretch. Even the boldest scientists hesitate to claim. So, the speed problem stays open, pulling researchers back toward the born big answer again and again. To really understand how these monsters got their start, you have to go back further than the dots themselves, to a time before any of them existed, when the universe was building its very first objects out of nothing but gas and darkness. Before the red dots, before the first galaxies, the universe was a dark, smooth fog of gas. For a stretch of time after the beginning, there were no stars at all, no light anywhere, just thin hydrogen and helium spread across space, slowly drifting in the dark. Scientists call this stretch the cosmic dark ages, and it set the stage for everything that came after, including the monsters in the dots. To build a giant black hole, you need a seed to start with. So, the question becomes simple. What was the very first thing that could collapse into a black hole, back when the universe held nothing but gas? The answer is the first stars, and they were unlike any star alive today. These first stars formed from pure hydrogen and helium, with none of the heavier stuff that stars contain now. That difference made them grow into giants. Some of the first stars may have weighed hundreds of times more than our sun, towering monsters of flame far bigger than anything that forms in the modern universe. They burned hot, burned fast, and died young, lasting only a few million years before collapsing. When one of these giant first stars died, it could leave behind a black hole heavier than a normal star black hole. That gave the universe its first seeds, scattered through the early dark. For a long time, scientists thought these star seeds were how every giant black hole began, slowly feeding and merging from these first dead giants up to the monsters we see today. The red dots suggest the story is bigger than that. Even the biggest first stars, when they collapse, leave black holes weighing maybe a few hundred suns. That is a decent head start, but the dots need black holes thousands or even hundreds of thousands of times heavier than that, and fast. Star seeds alone struggle to get there in the time available. The math keeps falling short, just like before. That is what pushed scientists toward the born big idea, where a giant gas cloud skips the star stage and collapses straight into a heavy black hole. In the cosmic dark ages, with thick gas everywhere and the right rare conditions, a cloud might have crashed down all at once into a seed weighing 100,000 suns from the very start. Those heavy seeds would have a far easier time growing into the red dot monsters, so the early universe may have made black hole seeds two different ways. The small way from dead giant stars, and the big way from collapsing gas clouds. The red dots might be the children of the big seeds, the rare giant collapses that gave black holes a massive running start while the universe was still young. Picture the difference like planting a forest. The small seeds are like acorns, tiny things that take ages to become trees. The big seeds are like dropping fully grown saplings into the ground, already tall, already ahead. A field of acorns and a field of saplings will look very different a few hundred years later. The red dots look like the saplings. Either way, something had to happen first to wake the universe up, to turn the dark, gas-filled cosmos into a place where black holes could form and feed. That awakening happened at a very specific moment, and it lines up almost exactly with when the red dots switch on. The red dots do not appear at random times. They switch on around 600 million years after the universe began, all across the early sky. That number is not a coincidence. It lines up with one of the most important turning points in the history of the universe, the moment the cosmos went from dark to lit. Remember the cosmic dark ages, when space was just a smooth fog of gas with no stars and no light. That darkness did not last. Gravity slowly pulled the gas into clumps, and inside those clumps, the first stars finally ignited. Then came the first galaxies, then the first black holes. Light spread across the universe for the first time. Scientists call this awakening cosmic dawn. Cosmic dawn is when the universe switched on, and the red dots appear right in the middle of it. That timing tells us something powerful. The conditions that lit up the universe, thick gas collapsing, the first giant objects forming, gravity pulling matter into dense knots, are the exact same conditions that build hidden black holes wrapped in hydrogen. The early universe was a factory for these dots, and cosmic dawn was when the factory turned on. The same era that made the first light also made the first monsters. There is a reason this moment could pump out black holes so well. Right at cosmic dawn, the universe was small and crowded. All the gas that is now spread thin across enormous distances was once packed into a much tighter space. Density was high, gas piled up fast, and in those dense, gas-choked surroundings, a collapsing cloud had plenty of fuel to crash into a heavy black hole and then keep feeding it non-stop. The early universe served black holes a constant, heavy meal. That density fades over time. As the universe expands, the gas spreads out and thins, like a crowd leaving a stadium after a game. Once the crowd thins, it gets harder to pile gas onto a black hole fast enough to feed a hidden, glowing dot. This helps explain the vanishing act from earlier, why the dots fade out roughly a billion years later. The thick, early gas that built and fed them slowly ran low, and the factory wound down. So the red dots are tied to a single chapter of cosmic history. They belong to cosmic dawn, the brief, wild window when the universe was dense enough and gas-rich enough to mass-produce hidden black holes. Before that window, the cosmos was too dark and smooth. After it, too spread out and thin. The dots mark the exact era in between, when everything lined up just right. That makes them more than a curiosity. They are a snapshot of the universe's most important growth spurt, the moment it stopped being a quiet fog and started becoming the structured cosmos of stars and galaxies we live in. The dots were forming right alongside the first galaxies, possibly helping shape them, all during this one explosive stretch of time. Catching this moment is exactly why Webb was built. It was designed to peer back to cosmic dawn, to the first light and the first objects. The red dots are some of the most surprising things it found there, proof that the early universe was even stranger and busier than anyone guessed. When scientists counted how many of these dots Webb was finding, the number itself became a shock, because there were far more of them than the universe was supposed to allow. When the red dots first showed up, scientists treated them as a curiosity, a handful of weird objects in a few images. Then they kept looking, and the dots kept appearing. Image after image, field after field. Everywhere Webb pointed into the early universe, more red dots turned up. The count climbed, and it climbed fast. The sheer number became its own problem. These dots are common in the early universe, far more common than anyone expected. In the patches of deep sky Webb studies, hidden black holes wrapped in gas seem to be almost everywhere during cosmic dawn. We are not talking about a rare freak object that shows up once in a great while. We are talking about a whole population, thick across the early sky, like a hidden crowd that nobody knew was there. That abundance breaks expectations badly. Giant black holes are supposed to be hard to make, especially this early and this fast. If they were truly difficult to build, we should see only a few of them in the young universe. Instead, we see a flood. The early cosmos was apparently cranking out massive hidden black holes in huge numbers as if making giant monsters was easy back then, when it should have been nearly impossible. Think about what that means. Whatever process builds these black holes, it was not a rare accident. It was happening over and over, all across the early universe. At the same time, a rare process makes a few objects. A common process makes a crowd. The dots are a crowd, which tells us the universe had some reliable, repeatable way to build giant black holes during cosmic dawn. This pushes hard on the Born Big theory again. Direct collapse, where a gas cloud crashes straight into a heavy black hole, was supposed to need rare, special conditions. Special conditions make rare objects. If the red dots are everywhere, then either direct collapse was far more common than scientists believed, or some other reliable black hole building process was running constantly in the early universe. Both possibilities mean we have been underestimating how good the young cosmos was at making monsters. The numbers also change how we think about the modern universe. If giant black holes were this common early on, then many of them should have grown up and survived. They would still be out there today, hidden inside galaxies, anchoring the structure around us. The crowd of dots in the early universe might be the childhood version of the giant black holes we find at the centers of galaxies everywhere we look now. A common early population would naturally lead to a common modern one. Counting the dots is tricky, and scientists are careful here. Webb only studies tiny patches of sky in extreme detail, then scales up to estimate the whole. Small samples can mislead, so the exact number of red dots in the early universe is still being pinned down, and the final count may shift as more of the sky gets surveyed. The basic finding holds, though. There are a lot more of these hidden monsters than the old rules predicted. A crowd of giant black holes blazing in the early universe is not just a counting problem. Objects that bright and that numerous connect to some of the most powerful beacons in all of space, the brightest steady lights the universe has ever produced. The universe makes a few objects so bright they outshine entire galaxies. We have known about the brightest of these for over 60 years, long before Webb existed. They are blazing points of light from the distant past, so powerful that early astronomers were baffled by them, the same way the red dots baffle us now. These cosmic lighthouses are called quasars, and the red dots are tied to them in a deep way. A quasar is a giant black hole feeding at full fury, with nothing hiding it. Gas pours into the black hole, heats up, and blazes so brightly that the single point of light outshines all the billions of stars in its galaxy combined. A quasar is the loudest, brightest version of a feeding black hole, screaming across the universe in every kind of light, including the X-rays the red dots keep trapped. Here is the link. A quasar and a red dot are the same basic engine, a giant black hole eating gas. The difference is the disguise. A red dot wears a thick hydrogen cocoon that traps the X-rays and softens the glow to a hidden red point. A quasar has shed that cocoon, exposing the raw, blazing black hole for all the universe to see. One is masked, one is unmasked, same monster underneath. That makes the red dots look like quasars caught at an earlier, hidden stage of life. Before a black hole becomes a roaring, exposed quasar, it might spend time as a buried red dot, feeding quietly behind its gas blanket. Then, as the cocoon thins and clears, the dot transforms into the brilliant, naked beacon we recognize. The screaming dot Chandra found, with X-rays leaking through gaps in its gas, would be a black hole right in the middle of that change, halfway from hidden dot to blazing quasar. If that is true, then the red dots fill in a missing piece of the quasar story. For years, scientists wondered how quasars got going so early in the universe. We found fully formed, blazing quasars when the cosmos was still very young, and just like the dots, they seemed too big, too soon. The red dots might be the answer. They could be the hidden childhood of quasars, the buried phase where the black hole bulks up in secret before bursting into view as a lighthouse. Picture a rocket on a launch pad, wrapped in scaffolding and clouds of vapor while its engines build up power. From a distance, you can barely see the rocket, just the haze around it. Then the scaffolding falls away, the vapor clears, and the rocket blazes upward, impossible to miss. The red dots are the rocket on the pad, engines already roaring behind the haze. The quasars are the same rocket once the haze burns off, and the full fire shows. This connection raises the stakes of the dots even higher. They are not a strange side branch of cosmic history. They sit right on the path that leads to quasars, some of the most powerful objects the universe has ever made. Understanding the dots could finally explain how the universe lit its brightest beacons so early. The same engine that powers quasars and red dots is sitting much closer to home than you might think. There is one at the center of our own galaxy, and it may have started its life as a hidden red dot, glowing in the young universe billions of years before Earth was born. Everything we have talked about has been far away, 11 billion light years out, in the deep early universe. The same kind of monster sits right here, at the center of the galaxy you live in. Our Milky Way has a giant black hole at its heart, and its story may have begun exactly like a little red dot. The black hole at the center of our galaxy weighs about 4 million times more than the Sunday. That puts it squarely in the size range of the red dot black holes, which run from 100,000 to 10 million solar masses. Our central monster fits right in the middle of that scale. It is the same type of object, the same kind of giant, just much closer and much older now. Today, our galaxy's black hole is calm. It sits quietly at the center, barely feeding, giving off only a faint glow. It is not blazing like a quasar or hidden like a red dot. It is mostly resting, with little gas falling in to make it shine. We only know it is there because we watch stars near the center whip around something invisible and enormous, circling a point of crushing gravity we cannot see directly. But it was not always quiet. Billions of years ago, when our galaxy was young and the universe was dense with gas, our central black hole was likely feeding hard. Back then, there was far more gas around to fall in, and that means it probably glowed, maybe blazed. In its youth, the heart of the Milky Way may have been an active, feeding giant, possibly even wrapped in a thick cocoon of gas, glowing as a hidden red point to anyone watching from across the early universe. If you could travel back in time and look at our galaxy during cosmic dawn, you might have seen a little red dot where the Milky Way now sits. The same buried black hole, the same hydrogen blanket, the same soft red glow. Our home galaxy could have been one of those mysterious dots, just another crimson speck in someone's deep field image, hiding the monster that would one day anchor everything around us, including the sun and Earth. Over billions of years, that hidden monster used up its nearby gas, shed its cocoon, and settled into the quiet giant it is today. The blazing youth faded into a calm old age. The dot grew up, and the galaxy grew up around it, building the spiral arms, the star clusters, and eventually the quiet corner where our sun formed and Earth came together. That connection makes the red dots personal. They are not just strange objects in faraway space. They are a picture of our own galaxy's distant past, a window into the violent infancy of the place we call home. The monster at our center carries a history, and the red dots may be showing us the opening chapter of that history, playing out in galaxies all across the young universe. So when scientists study these dots, they are partly studying us. They are tracing the early life of the very black hole our entire galaxy orbits around, the one that has been sitting at our center since long before there was anyone here to wonder about it. A quiet black hole can wake up, and when one of these giants starts feeding again at full power, the result is one of the most violent shows the universe can put on. A giant black hole does not stay quiet forever. Throw enough gas at it, and it roars back to life. When that happens, when a sleeping monster wakes and feeds at full power, it stops being a soft glow and becomes one of the most violent objects in all of space. This is the fully unmasked form, the destination every red dot is heading toward. We saw earlier that a red dot sheds its cocoon and turns into an exposed giant black hole. Now picture what that exposed monster actually does once the gas blanket is gone and it feeds hard. It does not just glow, it erupts, A black hole feeding at full fury does something strange with the gas swirling around it. Not everything falls in. Some of the gas gets caught in the chaos near the edge and flung back out, launched away from the black hole at staggering speed. The black hole's spin and crushing magnetic forces channel this escaping gas into two narrow beams, fired in opposite directions, straight out from the top and bottom. Scientists call these beams jets. These jets are some of the most powerful things the universe can make. They shoot out of the black hole at nearly the speed of light, blasting across space for enormous distances. A single jet from a giant black hole can stretch farther than an entire galaxy, punching out into space like a beam from a cosmic spotlight. The black hole, an object that traps everything, also fires out two of the fastest, most violent streams of matter in existence. That is the wild contrast at the heart of these monsters. The black hole itself swallows light and lets nothing escape. The gas around it, before falling in, gets whipped into blazing brightness and screaming jets. The most light-hungry object in the universe is wrapped in some of the brightest fireworks the universe produces. The red dots hide this fury behind their cocoons. The exposed giants let it loose. These jets do more than look spectacular. They reshape entire galaxies. A jet blasting out of a central black hole slams into the gas around the galaxy, heating it, pushing it, sometimes blowing it clean out of the galaxy entirely. By scattering and heating the gas, the black hole can shut down the birth of new stars across the whole galaxy, since stars need cool, calm gas to form. One black hole at the center can control the fate of billions of stars around it just by firing its jets. This is part of why the red dots matter so much. If these hidden black holes grow up into jet-firing giants, then they end up steering the galaxies they live in. They decide where gas goes, where stars can form, and how the whole galaxy takes shape. The quiet red glow we see now is the calm before a black hole steps into its role as the master of its galaxy. So the red dots sit at the start of a violent journey, from hidden red point to leaking screaming dot, to exposed blazing quasar firing jets across space, to the calm giant that finally anchors a grown galaxy. The dots are chapter 1. The jets are the wild middle, and our quiet Milky Way black hole is the peaceful ending, resting after a violent youth. All of this beauty and violence carries a darker side, and it is the reason the answer to the red dot mystery is described as bad news. Because what these dots reveal does not just amaze scientists, it threatens some of the deepest things we thought we knew. The title of this story promises bad news, and now it is time to face it. The red dots are thrilling, but their answer comes with a real cost. What these dots reveal does not just add a fun fact to astronomy. It tears a hole in the story scientists have been telling about how the universe grew up. The bad news is simple to state. Our timeline of the early universe might be wrong. For decades, scientists built a careful picture of how the cosmos developed after the beginning. First, the Dark Ages, then the first stars, then small galaxies slowly merging into bigger ones, with black holes gradually growing at their centers over billions of years. Everything in this picture happens step by step, slow and orderly. The universe builds its biggest structures patiently, over enormous spans of time. The red dots refuse to follow that schedule. They show giant black holes, millions of times the mass of the sun, already grown and feeding when the universe was only 600 million years old. In the careful, slow timeline, monsters that big should not exist yet. There was not enough time to build them. So either our timeline is missing a step, or the whole pace of early growth was far faster and wilder than we believed. Something major in our story is broken. This is why scientists describe the discovery as disruptive. It is not a small detail to patch. It strikes at the foundation, the basic question of how fast the universe assembled its first giant objects. If black holes could get this big this fast, then our models of the early universe, the ones we trusted for years, are leaving something out. We have to redraw the blueprint of cosmic dawn. Think of it like finding a fully built skyscraper in a photo of a city that was supposed to be empty dirt at the time. The skyscraper does not just surprise you, it proves your entire understanding of when and how that city was built is flawed. You thought construction took decades. The photo says it happened almost overnight. Now you have to figure out how, and your old assumptions are useless. That is the position astronomers are in. The red dots are the skyscraper in the empty field. They force scientists to admit that the early universe could build giant black holes in ways and at speeds the old rules forbid. The comfortable, slow story is in serious trouble. There is a deeper worry underneath all this. The way black holes grow is tangled up with the way galaxies grow, and the way galaxies grow is tangled up with the basic recipe of the whole universe, including the mysterious dark matter that shapes where everything forms. Pull one thread, and the others move. If the black hole part of the story is wrong, scientists have to check whether the galaxy part and the cosmic recipe part still hold up. One surprise in the early universe can ripple outward into everything. That is what makes the red dots more than a neat space mystery. They are a crack in the foundation, a sign that our grand story of the universe has a flaw in its early chapters. And a crack in the foundation means scientists have to go back and check the whole building. How serious is that crack? Serious enough that some researchers think it points at a problem with our biggest, most trusted model of the entire universe. Scientists have one grand model that explains almost everything about the universe. It describes how the cosmos began, how it expanded, how galaxies formed, and how it all fits together. This model has passed test after test for decades. It is the best description of reality we have ever built, and the red dots are poking at it hard enough to make some scientists nervous. The grand model rests on a careful schedule of growth. It says structure in the universe builds slowly, from small to large, over billions of years. Tiny clumps form first. They merge into bigger clumps. Those merge into galaxies, and galaxies gather into the vast web of structure we see today. Everything assembles, step by step, patiently, with no shortcuts. The model even predicts roughly how fast giant black holes should be able to grow inside this process. The red dots seem to break that schedule by showing giant black holes fully grown when the universe was barely getting started. The dots suggest structure assembled faster than the grand model comfortably allows. The monsters arrived too early. If the model is right about how slowly things grow, the dots should not be there yet. Their presence hints that either the model is missing something, or the rules of early growth are different from what we plugged in. Most scientists are careful here, and for good reason. The grand model has survived many scares before. Over the years, plenty of surprising discoveries looked like they might break it, only for scientists to find a clever explanation that fit the model after all. A new measurement, a missed detail, a process nobody had considered, and the crisis melted away. The model is tough. It has earned the benefit of the doubt, so the red dots might not actually break it. There are ways to keep the grand model and still explain the dots. Maybe black holes were born big through direct collapse, which the model can allow under the right conditions. Maybe they fed faster than we assumed during short bursts. Maybe our measurements of their mass are a little off, making them seem bigger than they are. Any of these could let the dots fit back inside the trusted model without tearing it down. That is exactly where the fight is happening right now. On one side, scientists who think the dots are a normal surprise, explainable with a tweak to the existing model. On the other side, scientists who think the dots are a warning sign, a hint that our grand story has a real flaw that no small tweak can fix. The argument is live, and the dots sit right at the center of it. What makes this thrilling is that we cannot yet say who is right. The red dots are new. The data is still coming in. Every fresh observation either pushes the dots back inside the comfortable model or pushes them further outside it. Scientists are watching closely because the stakes are enormous. If the dots truly break the grand model, it would be one of the biggest shakeups in the history of astronomy, forcing a rewrite of how we think the entire universe came to be. For now, The red dots are a question mark hanging over our deepest understanding of the cosmos. They might be a small puzzle with a tidy answer. They might be the loose thread that unravels part of the picture. Settling that argument is going to take more than Webb alone, and the next generation of telescopes is already getting ready to join the hunt. Webb cracked open the mystery of the red dots, but it cannot finish the job alone. To settle the biggest questions, scientists need more eyes on the sky, more kinds of light, and sharper views than even Webb can give. A new generation of telescopes is being built and launched right now, and the red dots are near the top of their target list. Each new telescope brings a different power to the hunt. Some are built to see even fainter and farther than Webb, catching dots too dim for it to study well. Some are built to survey enormous patches of sky quickly, so scientists can count the dots in huge numbers instead of studying them a few at a time. The more dots we catch, the better we can map when they switched on, how they behaved, and when they faded. One huge prize is finding more screaming dots, the ones leaking X-rays through gaps in their cocoons. NASA's Chandra telescope found one of these, the black hole caught halfway through shedding its disguise. That single object taught scientists how the transformation works. Finding more of them at different stages of unmasking would let researchers assemble the full life story of a red dot, frame by frame, like building a flipbook of the change from hidden monster to exposed giant. X-ray telescopes are key to that part of the hunt. The whole disguise depends on trapping X-rays, so the moments when X-rays start to leak out are the moments when the cocoon is breaking. New and future X-ray telescopes, sharper and more sensitive than what we have now, could catch dozens of dots in the act of breaking their disguise, instead of just one. Each one would be a snapshot of the change, and together they would reveal the whole process. Ground-based telescopes are joining too. A new wave of giant telescopes is being built on Earth, with mirrors far larger than anything before them, big enough to gather faint light from the early universe and study it in detail. These giants can work alongside the space telescopes, checking their findings and adding new measurements. The hunt for the dots is becoming a team effort across many telescopes, each covering a different weakness of the others. The goal of all this is to answer the questions Webb left open. How did the black holes get so big so fast? Were they born giant, or did they feed past the limit? Why do some dots go chaotic while others stay calm? Where do the dots go when they vanish? Are any of them the strange black hole stars some scientists suspect? Every one of these questions needs more data, and the new telescopes are built to gather exactly that. There is a bigger goal hiding behind the specific questions. Scientists want to know whether the red dots break our grand model of the universe or fit inside it after all. That answer will not come from one image or one telescope. It will come from years of patient work, gathering dot after dot, measuring each one carefully, slowly building a picture solid enough to test against our deepest theories. The new telescopes are the tools that will make that picture sharp enough to trust. So, the story of the red dots is far from finished. We are standing at the start of the real investigation, with better tools arriving every year. And the closer scientists look, the more they realize how much these tiny dots might be hiding, including answers to questions we have been asking since long before Webb existed. Step back from the details for a moment and look at what the red dots really represent. A few years ago, they did not exist in our minds at all. No one knew they were out there. Then a golden telescope unfolded in deep space, opened its infrared eyes, and revealed an entire hidden population of monsters that had been sitting in plain sight since the dawn of the universe. We went from total ignorance to a whole new field of science in just a few years. That is the part worth sitting with. The dots were always there. They had been glowing across 11 billion years of space the entire time, sending their light toward Earth long before humans existed. We simply could not see them. Every telescope we built before Webb was blind to them. They waited in the dark of our ignorance until we finally built the right machine to catch their light. It makes you wonder what else is out there, glowing patiently, waiting for the next telescope to reveal it. The red dots are a reminder that the universe is stranger than our models predict. Scientists had a tidy story about how the early cosmos worked, and the dots blew a hole right through it. They showed up where nothing should have been, behaving in ways the rules forbid, in numbers no one expected. The universe did not care about our careful schedule. It built its monsters its own way, on its own timeline, and left us to catch up. That humility is one of the most valuable things the dots have given us. Every time scientists feel confident they understand the universe, the cosmos finds a way to surprise them. The red dots are the latest and one of the biggest of those surprises. They prove that even our best models are works in progress, sketches of reality that need constant fixing as new light reaches our telescopes. There is something thrilling in that, not frightening. A universe that still surprises us is a universe with discoveries left to make. If we already understood everything, there would be nothing left to find. The red dots show us that the early universe still holds enormous secrets, and that we have only just started to read them. The story of how the first monsters formed, how galaxies were born, how the cosmos grew from smooth gas into the structure around us, is still being written, and the dots are a fresh chapter we did not even know existed. These dots also connect us to the deep past in a personal way. The black hole at the center of our own galaxy may have begun as one of these hidden red points. The quasars blazing across the universe may have started the same way. The giant black holes anchoring galaxies everywhere may all trace back to objects like these, formed in the wild early universe during cosmic dawn. The dots are not strangers. They are family, the infant versions of the monsters that shape galaxies, including ours. So, when you look at an image of the red dots, those tiny crimson specks scattered across Webb's deepest pictures, you are looking at the childhood of the universe's giants. You are seeing light that left before the sun was born, carrying the story of how the first monsters came to be. That story has one more turn left, one final idea about what these dots might ultimately mean for us and for everything we are still trying to understand. We have followed the red dots from their discovery to the edge of what science knows. We have seen them go from strange specks to hidden black holes to a crack in our understanding of the universe. Now comes the final question, the biggest one of all. What do these dots ultimately mean for us? The answer starts with where we came from. Every atom in your body, every bit of the earth, the sun, and everything around you traces back to the early universe. The first stars, the first galaxies, the first black holes all shaped the cosmos that eventually made us. If the red dots are part of how the first galaxies formed, then they are part of our own origin story. The processes that built these hidden monsters also helped build the conditions that, billions of years later, led to a small blue planet with life on it. That is the deep link. The red dots are not just distant curiosities. They are early steps in the long chain of events that ends with you, here, looking up at the sky and wondering about them. Understanding the dots means understanding a piece of how the universe set itself up to eventually make stars, planets, and people. The dots also change how we see our place in time. They show us a universe that was furiously active in its youth, building giant black holes and galaxies at a pace we are still struggling to explain. We live in a calmer, older cosmos now, with the gas spread thin and the great building era mostly behind us. The red dots are a window into the wild construction phase, the time when the universe was laying down the structures we now take for granted. We are living in the finished building, looking back at photos of it being built. There is a humbling truth in all of this. The universe was making monsters and shaping galaxies for billions of years before anything alive could witness it. The red dots glowed across cosmic dawn with no one to see them, no one to wonder, no one to name them. Only now, after all this time, has a species on one small planet built a telescope powerful enough to catch their ancient light and ask what they are. We are the first eyes to ever truly see them. That makes the red dots feel less like a problem to solve and more like a message finally received. Light that traveled for 11 billion years, carrying the story of the universe's youth, arrived at exactly the moment we had the tools to read it. A little later in history, and we would still be blind to them. a little earlier and we would not have the telescope. We caught the message right on time. What it tells us is that the universe is older, wilder, and more surprising than we ever imagined, and that we have only begun to understand it. The red dots cracked open a door into the early cosmos, and behind that door is a story still being told, full of monsters, mysteries, and questions we are only now learning how to ask. The dots gave us answers, and the answers gave us bigger questions. That is how the universe always works. Every secret it reveals points toward a deeper one, still hidden in the dark. There is one last thing worth saying about these dots, a final thought that ties the whole strange story together. We started this journey with a simple scene. A team of scientists crowded around their screens in 2022, spotting tiny red specks in the background of their first deep space images. They almost ignored them. The big galaxies were the prize. Those little dots seemed like nothing, just freckles on the face of the universe. Those freckles turned out to be monsters. Over 4 years, scientists pulled an extraordinary story out of those specks. Each dot is a giant black hole, weighing up to 10 million times more than the Sun, hiding inside a thick blanket of hydrogen gas. The blanket traps the black hole's violent X-rays and lets only a soft red glow escape, a glow stretched even redder by 11 billion years of the universe expanding. The dots switch on during cosmic dawn, thrive for a while, then vanish, growing up into the ordinary giant black holes that anchor galaxies today, including our own. That is a stunning amount of understanding to pull from a few points of light. And the team did it without ever leaving Earth, just by reading the ancient light those dots sent across the cosmos. The red dots also handed scientists a problem they cannot ignore. These black holes are too big, too early, breaking the careful timeline of how the universe was supposed to grow. They may have been born giant, collapsing straight out of enormous gas clouds, skipping the slow growth everyone believed in. They might even threaten our grandest model of the cosmos. The answer to the red dot mystery solved one question and opened a dozen harder ones, which is exactly why the discovery matters so much. Here is the thought that ties it all together. The red dots prove that the universe is full of things we cannot yet see. They were always there, glowing across the early cosmos, completely invisible to us until we built the right telescope. For the entire history of astronomy, an entire population of monsters sat hidden in our images, waiting. One new machine, tuned to the right kind of light, and suddenly they appeared everywhere. That should fill you with wonder, not worry. It means the universe still has enormous surprises in store, secrets glowing in the dark, waiting for the next telescope and the next generation of curious minds. The red dots are proof that discovery is far from over. The cosmos is still hiding its biggest stories, and we have only just started to find them. So the next time you see one of Webb's deep images, with thousands of galaxies scattered across the black, look closely at the tiny red specks in the background. Each one might be a giant black hole, a monster from the dawn of time, sending its ancient light across the universe to reach a small planet where someone finally looked up and wondered what it was. The little red dots traveled 11 billion years to reach us. They carried the story of how the universe built its first giants, how galaxies were born, and how the cosmos grew from darkness into light. We almost overlooked them. Instead, we turned around, looked closer, and caught one of the biggest mysteries of the early universe glowing quietly in the background of a photograph. The universe was hiding its monsters in plain sight. Now we know where to look,